Welcome back. Today we're diving deep into the world of global energy transport, looking at some really specialized engineering, stuff that's usually hidden beneath the waterline of every major LNG carrier. We are talking about containment, that crucial technological barrier that makes shipping liquefied natural gas, or LNG, possible, safe, and, well, profitable.
It really is a hidden marvel. We're dealing with methane cooled way down to a super cryogenic temperature, about minus 163 degrees Celsius. And it's held at pretty much atmospheric pressure. The simple truth is, if you don't nail the containment system, the whole operation just fails.
Right.
Safety is absolutely paramount, obviously. But right behind that is this constant battle against heat getting in. You need total leak tightness, you need structural resilience to these huge temperature swings, and all while minimizing that heat ingress so you don't just boil away your valuable cargo.
Okay, let's unpack this. Our mission today is really to get into the GTT Mark III membrane system. This specific technology has become, well, pretty much dominant globally. We want to understand how GTT manages to balance that absolute safety and the flexibility needed with the tough demands of high-volume shipping economics. We'll try and trace its evolution, maybe from the early ideas right up to the advanced versions we see today.
Yeah, it's a fascinating story. When you look at the LNG fleet out there, you generally see two main styles of containment. There's the Moss type. You can spot those easily. The big, distinctive spherical tanks sitting prominently on the deck. They're structurally independent of the ship's hull itself.
Yeah, the big balls on deck. I know the ones. But most ships don't look like that anymore, right? The majority, especially the newer ones, rely on these membrane systems pioneered by GTT.
Precisely. And that points to the key commercial advantage of the membrane design. They let you maximize the cargo volume you can fit within a given ship shape, the hull form. They essentially line the inner hull of the ship with the insulation and then this barrier system. This space-saving approach minimizes the ship's weight when empty the light ship weight. And that translates directly into much better transportation efficiency. GTT, that's Gas Transport and Technogas, they hold the patents, the IP for this tech, and yes, it's absolutely become the de facto standard for nearly all LNG carriers being built today.
That dominance is really interesting. It basically means the success of GTT's engineering directly impacts the cost of shipping natural gas all over the world. They really had to get this right. Now, we know the Mark III wasn't their first shot at this. What were the hurdles with the earlier systems?
Well, they sort of inherited two different design paths, and both had their challenges, commercially speaking. One side, Mark I and II, used corrugated stainless steel, but it turned out to be quite complex to fabricate reliably in the shipyard. The other lineage, the CS1 system, used a different material, a nickel-iron alloy called Invar. Now, Invar is pretty amazing stuff because it has almost zero thermal expansion. It barely shrinks at all when you cool it right down.
That sounds perfect. Like the ideal material for holding something super cold. Why move away from that?
Because it was, frankly, a nightmare to work with in a shipyard context. Invar is incredibly expensive, and it needed very specialized, difficult welding techniques, plus super strict quality control. All that made construction slow and pushed the costs way up. The industry needed efficiency, faster build times. So the Mark III was kind of the genius compromise. It brought back the corrugated stainless steel idea, which is cheaper and easier to handle than Invar, but paired it with these clever modular insulation panels for much faster installation in the yards.
Okay, let's zoom in on that steel then. The actual membrane, the bit holding potentially millions of gallons of this ultra-cold liquid gas.
Yeah.
It's only 1.2 millimeters thick. That seems astonishingly thin. And the core innovation, as the sources really emphasize, is the corrugation.
Exactly. Think of it like a metal accordion, or maybe the waves you see in corrugated cardboard. That's fundamentally what the Mark III primary barrier looks like. It's wave-like.
But wait, if you make a 1.2 millimeter sheet of steel flexible like that, doesn't that inherently make it weaker? How does that wave pattern give it the strength and, crucially, the tightness it needs?
Yeah, it feels counterintuitive, doesn't it? But the flexibility is the key to its strength in this application. See, when you cool that huge tank structure down from ambient temperature to minus 163 Celsius, the steel wants to shrink dramatically. We're talking maybe several centimeters of contraction across the width of a big tank. If that membrane was just a flat sheet, that thermal shrinking would create immense stress points.
I see. It would just tear itself apart.
Eventually, yes. Or it would lead to fatigue cracks, brittle failure. The corrugations act like built-in expansion joints. They accommodate that massive thermal expansion and contraction simply by flexing the waves flatten out a bit or get deeper. It's a mechanism designed specifically to stop the steel from building up dangerous stress levels and to maintain that critical leak tightness through every cool-down, warm-up cycle, every time the hull flexes at sea and under all the dynamic loads.
So the flexibility is absolutely key for survival. But given how incredibly thin that primary barrier is, safety redundancy must be a massive priority. I know the international rules, the regulators, insist on a dual barrier system.
Oh, absolutely non-negotiable. The IMO IGC code, that's the International Rulebook for Gas Carrier Safety, mandates it. You have the primary barrier, the corrugated steel containing the LNG, but behind that, you must have a secondary barrier. It's the ultimate fail-safe. It has to be impermeable itself and strong enough to safely contain the cargo for a reasonable period, long enough to get the ship to port if the primary barrier were somehow compromised.
What kind of material provides that critical backup? Is it another steel layer?
No, it's actually quite different. The secondary barrier is typically a sophisticated composite membrane. It's often called triplex. Essentially, it's a thin layer of aluminum foil that's laminated, kind of sandwiched, between two layers of glass cloth that's been reinforced with a polymer film. It's light, surprisingly tough, and completely impermeable to the gas. And crucially, the space between the primary steel barrier and the secondary triplex barrier, the interbarrier space, is constantly monitored.
With sensors?
Yes, exactly, using gas sensors. This space is kept at a slight underpressure usually and continuously monitored. It acts as the early warning system. If there was even a tiny microscopic leak in the primary steel membrane, you'd detect traces of methane gas in that space long before the secondary barrier itself was ever structurally challenged.
Okay, that makes sense. Early warning is vital. Now, we've talked about the static containment, but what happens when the ship isn't just sitting still? When it starts encountering rough seas, getting tossed around? Let's talk about sloshing. Sloshing. Yes, that's a major dynamic challenge.
Yeah.
Sloshing refers to the dynamic loads generated by the liquid cargo moving inside the tank when the ship pitches, rolls, or heaves, especially in heavy weather. If the tank is only partially filled, say, anywhere between maybe 10% and 90% full, the liquid can behave like a giant uncontrolled wave inside the tank. It builds up tremendous kinetic energy and can slam against the tank walls and the internal structures with really extreme localized forces. This can potentially damage the insulation panels, which, remember, are supporting that thin steel membrane.
That sounds pretty violent. So how does GTT prove that their containment system, including the insulation, can actually handle that kind of abuse?
It requires really intense engineering validation. They do exhaustive physical model tests. They build scaled-down sections of the tank. Then they put them on motion platforms that simulate violent ship movements. And they measure the impact pressures, the loads. And they couple all that physical testing with very sophisticated computer simulations, CFD, computational fluid dynamics. This ongoing testing and simulation work is really what drives the evolution of the system over time.
Which brings us nicely to those refinements you mentioned earlier, like Mark III, Flex, and Flex Plus Width.
No.
What drove those specific changes?
Exactly. The need for even greater resilience, particularly in the insulation panels and their supporting structure, led to these iterations. The Mark III Flex introduced some modifications to the geometry, which also helped speed up assembly in the shipyard and offered slightly better tolerance to deformation. But the Mark III Flex Plus WA, that was a more significant step. It specifically integrates enhanced insulation components and structural reinforcements designed to beef up the system's resistance against those high sloshing loads we just talked about.
Yeah.
This became especially vital for the new generation of very large carriers and also for specialized ships like FSRUs.
FSRU.
Floating storage and regasification units. These are basically floating LNG import terminals. They often stay moored in one location, sometimes in quite harsh coastal environments, for years, so they have to deal with liquid motion inside their tanks constantly. Perhaps more predictably than a trading ship, but definitely persistently. So sloshing resistance is critical for them.
Right. Okay, here's where the engineering connects directly to the money side, the bottom line. Boil-off gas, or BOG. We talked about the insulation being key. These panels are complex, right? Often layers of high-density foam, maybe plywood, sometimes traditional balsa wood. If the insulation is supposedly so good, where does that tiny bit of heat still manage to creep in, and why does that resulting boil-off gas matter so much economically?
Yeah, no insulation is absolutely perfect, especially not over the scale of a massive ship tank and a voyage that might last thousands of miles. So inevitably, a very small amount of heat does leak through the insulation layers. This minimal heat ingress causes a small percentage of the LNG, the liquid methane, to vaporize back into gas. That's the boil-off gas. Modern vessels, especially those with Mark III systems, aim for very low BOG rates. Typically, the target is somewhere between 0.085% and maybe 0.10% of the total tank volume per day.
Okay, 0.1% per day. That still sounds pretty tiny. Can you put that into perspective? Like, what does that actually mean in terms of lost cargo, lost revenue on a typical long journey, say 20 days?
Well, it might sound small, but it's definitely not negligible when you scale it up. A big modern carrier, like a QMax, holds around 266,000 cubic meters of LNG. If you lose even, say, 1.5 to 2% of that cargo to boil off over a 20-day voyage, well, depending on the fluctuating price of LNG, that could easily represent millions of dollars worth of lost revenue per trip.
Wow. Okay, yeah, that adds up fast. Millions per trip.
Exactly. So minimizing BOG is crucial for the economic viability of the whole operation. Fortunately, the technology around it has adapted too. Modern ships often have advanced dual-fuel engines, things like the MEGI, the XDF, or older DFDE systems. These engines are specifically designed to efficiently burn that boil-off gas as fuel for the ship itself. So you minimize the actual cargo loss, you reduce the need for other fuel oil, and it also helps meet environmental regulations like MARPOL by reducing overall emissions. It's become a really integrated efficiency and environmental solution. Some ships even have reliquefaction plants on board to turn the BOG back into liquid.
That's clever, using the waste product. Okay, speaking of efficiency, let's touch on manufacturing. The sources highlight this use of modular construction. Building these incredibly complex systems inside a massive steel hull sounds complicated.
It is, but it's become a highly industrialized process. The insulation panels themselves are largely prefabricated. They're built in specialized, climate-controlled factories, often with very strict control over the materials, whether it's the traditional balsa wood or the newer foam and plywood composites. They're manufactured to extremely tight tolerances and then delivered as ready-to-install modules to the major shipyards, particularly the big ones in South Korea and China that build most of these vessels. This modular approach allows for rapid, predictable assembly inside the ship's hull. That's a huge factor in cutting down the time and the cost it takes to build one of these very expensive ships.
Right, speed and consistency. So once that whole complex structure, the insulation and that thin steel membrane is all installed, how do you absolutely guarantee it's leak tight? Especially for a system that needs to last for decades under immense stress.
The quality assurance, the QA process, is incredibly intense. It's multi-layered, and it's all overseen by third-party classification societies. You know, organizations like ABS, DNV, Lloyd's Register, BV, Class NK, they set the standards and verify compliance. First off, the materials themselves undergo rigorous testing before they even get near the ship. The stainless steel, for instance, undergoes cryogenic testing. Samples are plunged into liquid nitrogen down at minus 196 degrees C just to make absolutely sure they retain their toughness and resist becoming brittle at operating temperatures.
Okay, so you test the raw materials. What about the actual construction on the ship? All those welds and seams joining the steel membrane sections together.
That's where the helium leak test comes in. This is really the ultimate non-destructive test for the primary barrier's integrity once it's installed. Why helium? Because helium atoms are incredibly small. So sections of the completed primary barrier are carefully pressurized with helium gas. Then technicians use highly sensitive instruments called mass spectrometers to essentially sniff along all the weld seams and surfaces. They are looking for the tiniest trace of helium escaping. Even a microscopic imperfection, a pinhole you couldn't possibly see, would allow some helium through, and the mass spectrometer would detect it. You're literally scanning to ensure the entire system is airtight, down to a molecular level. It's painstaking, meticulous work, but it's absolutely non-negotiable for safety.
That level of microscopic precision is just remarkable. So thinking ahead, where does this containment technology go next? What are the big challenges engineers are tackling for the next generation of these systems?
Well, a major driver continues to be the pursuit of even lower BOG rates, pushing the boundaries of insulation performance further and further. We're seeing active exploration into more advanced high-performance insulation materials, things like aerogels, maybe used in hybrid solutions with existing foams, and definitely a big push towards finding sustainable sourcing alternatives for traditional materials like balsa wood, which has faced criticism regarding deforestation and its environmental footprint. Sustainability across the whole life cycle is becoming a huge focus.
Right, greener materials. And what about the digital side? Are these tanks getting smarter?
Absolutely. The trend is definitely towards smart systems. We're seeing the integration of dense sensor networks embedded within the insulation and barrier layers themselves. These sensors can provide real-time monitoring of temperature gradients across the insulation, pressure fluctuations, maybe even detect strain or potential microleaks developing. This data allows a shift in maintenance philosophy, moving away from just scheduled inspections towards condition-based monitoring. Ship operators can potentially identify and predict issues based on real-time data rather than just waiting for a scheduled check or, worse, a failure.
And I guess that ties into the idea of a digital twin.
Precisely. Creating these detailed digital twins, essentially, virtual computer replicas of the physical tank structure and its systems. This allows engineers back on shore, or even the ship's crew, to run advanced simulations. They can stress test the virtual structure under theoretical extreme weather conditions, predict where fatigue might start to occur years down the line based on the ship's actual operating history.
Okay.
It's all about using data science to maximize the operational lifespan, optimize performance, and enhance safety margins even further.
Okay, fascinating. Finally, as the world looks towards an energy transition, LNG might eventually share the seas with even more challenging cargoes. What needs to change fundamentally in the Mark III concept or its successors to handle future fuels like, say, liquid hydrogen or ammonia?
That's a huge adaptation challenge, and GTT and others are definitely working on it. Liquid hydrogen, LH2, is far more extreme than LNG. It needs to be stored at minus 253 degrees Celsius. That requires a completely different level of insulation performance. And because the hydrogen molecule is so much smaller than methane, the requirements for leak tightness become orders of magnitude more stringent. Any tiny imperfection is more likely to leak. Ammonia, NH3, isn't quite as cold, but it brings its own challenges. It's highly toxic and can be corrosive to certain materials, so the barrier materials themselves need to be carefully selected or adapted to withstand its chemical properties over the long term. So, while the fundamental principles of dual barriers and managing thermal contraction still apply, significant material science and engineering adaptations are needed. GTT is already developing specific Mark III derivatives designed to tackle these new, very challenging energy vectors. So if we were to boil it all down, the key takeaways really are: the GTT membrane system is this elegant balance achieving flexibility through that corrugated steel to handle the extreme cold contraction, ensuring absolute safety with the mandatory dual barrier system, and driving economic efficiency through sophisticated insulation that minimizes that costly boil-off gas. The evolution, the iteration to flex and flex plus steer, that's been a direct result of learning from real-world operations, especially the need to better manage sloshing forces on bigger ships and FSRUs. And looking forward, the future of containment seems to be about integrating smarter monitoring sensors, digital twins, and adapting these proven principles for the even tougher demands of future fuels like liquid hydrogen.
It really is incredible. The ultimate success, I think, of the Mark III system is how it makes something that sounds technically improbable, carrying vast quantities of liquid gas at minus 160 degrees Celsius across huge turbulent oceans, seem almost routine now. And when you pause and consider the sheer geopolitical reliance we have on these specialized ships for global energy security, the quiet, hidden reliability that's guaranteed by all that complex quality control, the cryogenic tests, the sloshing models, the painstaking helium leak detection, that reliability is truly the unsung engine of the global